Good morning, everyone. Let's start the lesson with Professor König, who will teach us more about Symmetry-Protected topological model.
Right, thanks so much for coming. Yesterday, we introduced the path integral for a single spin on our way to describe symmetry-protected topological phases using field theory. So field theory means that, in this case, we're doing a path integral formalism. So the field is this n of tau, and we derived, or at least motivated using this factorization approach, we motivated the following partition sums. So to get the partition sum, we have to integrate over all possible field configurations of these fields n, deliver the sphere, and they describe simply the orientation of your spin. And there are boundary conditions, which is that this field n is a function of tau, imaginary time tau. That is sort of periodic. So n of tau, n of 0, tau equals 0 is n of beta. And there are two terms in the action. One term is just the Hamiltonian. The original Hamiltonian was written in terms of the operator. So originally this was something like a of operator S for a spin S particle, and then the same functions, but not with this operator in it as an argument, but with S times this unit vector, is what enters this part of the action. And then we had the second term, which was the Zumino term. That's Zumino. And this term is in some way topological in nature, and it measures the Berry phase enclosed in the time evolution of this spin. So as I said, what we have a mapping. So since the boundary conditions are such that the 0 and beta are identified, what we're effectively doing is when we have we have time going from 0 to beta. But this point equals this, so this is actually the same as this. 0 and beta being the same. And we are mapping this, so we have this tau is being mapped to n of tau, so that values on the sphere. And that means that we are tracing some contour on the sphere, and that's exactly what's drawn here. So we are tracing the field configurations, tracing certain contour as a closed loop on the sphere. And what this term here does, it measures the solid angle enclosed in this contour. And as we discussed yesterday, there are two ways of calculating the solid angle. It's either the solid angle marked in red here, or the solid angle marked in green. As it goes around this area corresponding to the solid angle, it acquires a flux. And the flux is corresponding to a monopole sitting inside the sphere and having a field which is radially pointing outward. The particle has charge S in this position. So we've mapped this problem of spin to a problem of a charged particle on the sphere, and the sphere has a monopole inside it. Okay, and therefore it acquires flux, and that's exactly why we measure the solid angle, either the red or the green one. And then we also discussed that there should be no difference for any physical quantity whether we calculate the solid angle using the red area or the green area. And when you take the difference of the two, you realize that essentially what you have to do is to take the integral of the whole sphere. That leads to a topological quantization condition of the prefactor of this integral. So this is a topological term in which the integral itself is not quantized. It just measures this area, or the green one, doesn't matter. But the prefactor is quantized due to topological reasons. And in fact, in this case, what we retrieve is that the only spin quantum numbers which are consistent with this construction are half integers. So integers and half integers. That was yesterday. We then also discussed other types of topological terms. Some which are such that instead of having the prefactor necessarily quantized, we have the integral being quantized. These are called theta terms, and we're going to see one appearing in a second.
Is this the same argument that you use to say the electric charge is quantized? Like if there were negative monopole, then electric charge is quantized. Is this the same exact argument?
I don't know if it's the same exact argument.
Like the fact
I know that there are such arguments, and they're probably similar in nature. And I will think. It might well be, yeah. Yeah, I don't know. Okay. So we're now speaking, we're returning to the problem of antiferromagnetic spin chains. 7.3. Antiferromagnetic spin chains. So you remember that we studied at some point, this is a reminder, we had a brief chapter in which we studied spin chains, and we found that spin 1 chains allow for SPT with spin 1 H states. And we had explicit or exact solution, explicit construction. We studied this when we added, in addition to having antiferromagnetic nearest neighbor interactions, we added these biquadratic interactions in the AKT model. So that's chapter 3. So now we're going to revisit the same problem, but from the perspective of field theory. We actually also, we're studying for the moment arbitrary S, including half integer S. You will see the difference between half integer and integer, but we will also return to the situation of spin 1. So what we're doing is we're looking at a Hamiltonian of this type, antiferromagnetic interactions, and nearest neighbor hypergraph. So these are spin S operators as before. And what we're going to do is we're calculating this thing here, the effective action, using the same prescription that we've used before. But here we did it for a given spin, one single spin. Here we do it for a bunch of spins. Let's say L spins. That's one spin. And on each side, we do the prescription that we did. So what you then get is S equals, maybe I write it like this, SH plus S top. SH is nothing but integral tau from 0 to beta, uses at each side I. So we sum from I equals 1. Well, let's say very boundary conditions. So we can also open the boundary conditions, doesn't really matter. We have S squared J and I plus 1. also write this up to a constant as s squared half minus plus s squared j half integral d tau sum of all I and I plus 1. I can also do it like this plus the constant is not important. Okay, it's just keep it's important when it's just a cross term when you factor out the product. Okay, and then there is the S stop. That's just for each of those guys this term. For each position, this term, so we have IS integral d tau 0 to beta sum of all I Ni, of course it depends on how times A, I. Because A depends on Ni. And so, maybe another comment. We have seen this, I mean, last time I showed you explicitly, I wish I can write it down again. This A here is explicitly expressed in terms of theta and phi, the angles that we chose to represent n. So it does depend on n in this way. And let me also emphasize that it is characteristic for this measurement that essentially, if you want to write them down concisely, they are parametrization dependent. Like so. So you see the phi and the theta explicitly. And if I had taken different phi's and theta, maybe, of course, the physical thing does not depend on this, but the expression in the integrand might actually reflect it. If Pasha will speak more about the Zamino terms with you, I would guess in the context of the quantum Hall edge states, then you will see more of this. Okay. So we have this multiple topological term and this energetic term. And now what we want to do now is we do a procedure of finding a semi-classical solution and then looking for fluctuations, quantum fluctuations about the semi-classical solution. And to find the semi-classical solution, we need a small or a large parameter. In this case, the large parameter is S. So as we send S to infinity, we want to minimize this energy. And then the ends have to be staggered to get an AL state. So the classics. This S goes to infinity. And I is first of all time independent. And so the minimum is time independent. And a unit vector that I call D. Does everybody know, maybe I should say this, why is S goes to infinity semi-classics? I mean, on the level of this action, you see that S goes to infinity. Okay, so maybe not everybody is aware of this. So when you have this action formalism, what we do here in quantum theory, we integrate over all field configurations, and each of them has their weight. But there are field configurations at which this S here is, let's say, minimal or at least extremal. In this case, we're looking for minimum. These are the contributions which are strongest in this field integral as S goes to infinity. At the same time, these are the solutions to the semi-classical equations of motion because you minimize the action. That's what you learned in analytical mechanics. So that's why it's called semi-classical in the context of field theory. But there's also another reason why S to infinity is semi-classics, because remember that SA, SB is I, A, B, C, A, B, C, SC, right? This is the spin commutation algebra. It makes sense to define little s, A, which is SA divided by little s. And then you see that I have to get a computation algebra of little s's. Little s, A, little s, B is I, epsilon, A, B, C. And then you get little sc divided by s. If you wish, I can also add h bars. I think there's an h bar here, but never know. There should be h bar here. So you see, h bar goes to 0 and s goes to infinity is the same. It removes the non-trivial part of the commutation. That's the variable smooth. So s goes to infinity is the same as taking this. This is from the perspective of operators, and what I said before is from the perspective of feeding flow. Okay. Next step is to look for so this is near state. Next we look for fluctuations about, so what we want to do now is we found a symmetry broken state, and what we want to see is what are the Boltzmann fluctuations around the symmetry broken state, and are they allowing for such a state to exist essentially or not, right? So you know that in low dimensions here we're speaking about one spatial dimension, quantum and also thermal fluctuations, in this case quantum fluctuations, prevent actual long range work, even if on the mean field level you do find long range work. So this is if you want mean field. The semi-classics is the same as mean field.
Are the large S total spins and the small S individual spins?
So we have each of those guys here. So here this is the path integral for a spin S particle. This small s here. And what we looked at is a bunch of L spin S particles along a chain. So the number of spins is L, their size is S.
Yes, and these large S's are the normal spin operators.
These here, yes. These are the components of this S. And they are spin S representation. So it makes sense to study the commutation relation sort of normalized to the sign of the vector. That's why I went to small s's. And this is the commutation relation of the small s operators. This is something that is in so these little s's essentially they are Casimir, so s squared goes to 1. Right? Because the s capital S squared goes to s at s plus 1 and divided by s squared, so the whole thing goes to 1 as s goes to infinity. So when you take these limits, you want to sort of rescale things appropriately so that you can compare apples and oranges. Okay, so now we want to look at fluctuations about this mean field solution, or semi-classical solution. So we're doing this, we're taking actually now a little bit a slightly more general situation. So, sorry, this d here is actually position dependent. It's -1. Oh, so it's -1 to the I, and then a vector d. So it means that we have a staggered state. Up, down if d is dc. Or maybe whatever, right, left if d is dx. So now we take an I of tau with spatial and temporal fluctuations. So we take -1 to the I times d. Now we allow d to be dependent on the position I, which I write as xi here in the brackets, and tau. And then we take plus 1 over s fractions L xi and tau. So the assumption on this L is L is perpendicular to D, and L squared is order 1. So these are transverse fluctuations. So maybe I cannot draw something in 3 dimensions, but in order to illustrate it, maybe let me draw the Mexican pattern, like for a problem with a smaller order parameter manifold. So the L essentially are fluctuations of this type, and the D fluctuations live on the manifold of right? So the D's, they are still normalized. And yes, the width is essentially what we're looking at. So the L's are fluctuations about, which are sort of, they're going to be massive, you will see in a second, they will be massive. And we're doing things, everything that I'm doing is order by order in 1 by S. So from this you will see that N squared is going to be 1 plus order 1 by S squared. I would need to do additional constraints on the L to make it exact, but it's sufficient for me to work this way.
Right. So if you're writing perturbations theory of like 1 over S, then why D became wording at that time dependent?
Just not only there. So what we do is we're looking at, we start from a configuration, which is an L state. And there are things that we're looking at which are smooth spin waves. So let's say I rotate this guy a little bit, but at the same time I rotate this guy a little bit. But I do it only smoothly, so this guy is already rotated less, and this is even rotated less, and this is already rotated not at all. Such a configuration is in the D. So we have made the D slightly x dependent. It's still very close to the linear state, but it's x dependent now. Right? Or if you wish, the whole black arrows can rotate in time. That's also in the D. And then there are other things that could happen. For example, this does this, and this does this. Or something like this. So these are modes where they do like this. This is something that's in the L. Is that your question now?
But that should also be 1 over S corrections. Or am I wrong?
You're asking whether ultimately in the action everything is going to be 1 over S corrections to the
yes, exactly. So I thought that
that's right, but on the other hand,
should be incorporated in L and not in D.
So okay, so these first of all, I need to make a unit vector somehow, right? So I cannot make this here 1 over S, otherwise it's not going to be 1 when I square it. So what I'm doing is, so when I do this procedure, you will see that we get an action, in the end we get an action which has S as a prefactor, and it has gradients of D field. And when you then try to calculate the partition sum, you will get corrections to the partition sum, which are order by order in 1 over S, due to the fluctuations. So you can use this to organize perturbation theory. You can still use large S and fluctuations in these D fields, spatial fluctuations, to organize the perturbation theory or the renormalization. Okay. Let's plug this into the H, SH. SH. I should also say this guy is smooth, yeah? So this guy is smooth, meaning that it's slowly varying in space. So we will do an expansion not only in 1 over S, but also in gradient in D. So we have Js squared A half times dx. This is only x dependent, so I'm now switching to, I'm switching already to continuum dx n, sorry, d square. And then the L. So you note that this here is minus 1 to the I. This one does not. Right. So therefore it will add up over there. And what we get is 2j over A a lattice spacing A. The lattice spacing A. The lattice spacing is here. This is A. And what I've done is I've expanded this D. So when I have dx plus A minus dx, that's what I have here, right? Because they have opposite sign because the minus 1 to the I. So I get effectively a difference of these d's. Right? I write this as A dxd of x, approximately. And what I also use is that sum over all I A will be replaced by dx. It's a Riemann integral function.
Excuse me?
Yeah.
Remind me please, what is n and d operator?
What is n and what is d operator? Yeah? Okay. So the n operator is the field, well, I'm not sure if you call it the operator. It's the field of each of these spins and can take any value in the unit spin. And what I'm doing is now, so I implicitly integrate over all of these configurations, including ones which are very rough in space, like where they do something very, very different. But then what I want to do is I want to concentrate on the vicinity of the minimum of the action. So I found that this is minimizing the action, because it makes this term here vanish. And so we have minus 1 to the I and d, the same d everywhere, and this is just vanishing completely. So now we're going here, we know that, so this here is the full field, but we're replacing it, if you want this as an approximation. We're only taking into account small fluctuations about the semi-classical resolution. This means that the d we allow for small fluctuations, spin waves, which I had represented in I did the wrong color coding. So the red one is the smooth configuration, which is done in the D here. And then there are configurations which are completely going out of the scheme. So the D is a smooth field, and the N is something that can take anything.
And what is n?
And L after, so L, again, wrong color coding. L are operations, so the red one will be what the D is, which is only smooth configurations about the near state. The L does something drastic, for example, letting these guys go in opposite directions or in opposite directions this way.
Okay.
So you can see this by seeing that the condition that L is perpendicular to D is essentially the condition that these are going to be massive operations. And you see explicitly when you plug this in there, you take this square, obviously the D and L cross terms vanish because of orthogonality by construction. And then what you see is that the L term here has no gradients while the D term has gradients. So when the D is spatially independent, we go back to the minimum of the action. But the L even is spatially independent, it will always cost energy. So therefore we call this here a massive mode, or actually it's two massive modes because there are two modes which are perpendicular to a given D. This. But then this here is a massless mode. So the D will be the Goldstone mode, goes on, and the L is somewhat similar to these guys here as a mass. This here is really, this is only a very loose analogy, but it's sort of giving you an idea. Okay, so we already know what happens to the SH. Now we need to know what happens to the S top.
Is the gradient of D also for the 1 over S or not necessarily?
Not necessarily. Well, the gradient of D is just the gradient of D. But then you can ask the question later, if you wish you can sort of absorb these S's in here. And then this makes it effectively 1 over S. So what I want to say is that energetically, probably gradient of 1 over S will only be an But a priori it's anything. Okay, so the topological term was this sum over all I S the domino of. Okay, we have two terms here. Maybe they go a step back. Well, I can write it out like this. So this was as a domino of Ni. I need an extra line. So we need Ni dot A of Ni. And we use this parameterization of our Ni's. So then, order by order, you get, first of all, the order from just the d's. Minus 1 to the I, d dot, times A of minus 1 to the I of d I. So, okay, anything is going to be a, so as a precedent index, I of the d's, but in principle they're also x I dependent and tau dependent. Then there are going to be 1 over s corrections. And these 1 over s corrections occur by either taking so we have either here we can place the n part, or here we can place the n part, right? So anywhere I put n is minus 1 to the d, minus 1 to the id plus 1 over sl. So now I can put here 1 over sl times a, evaluate the d, or reverse. So we get this next term, and we only keep 1 over s terms. Sorry, I need to write this in blue. Plus 1 over s. So for example, we have L dot times A of minus 1 to the I d. And then we also have plus minus 1 to the I d dot. And now we have the A, but only the A part coming from the L. So what I do is actually, I write this out in indices. How this is going to be clear in a second. The B A of minus 1 to the I D L B. So effectively, maybe I should write it out. So what I used here, I had this, right? AA of minus 1 to the I D plus 1 over S L. I write this as AA of minus 1 to the I D plus, and now I just do a Telex function, dB of AA of minus 1 to the I d d LB. So this term is this term, and this term here is the one I'm ending here. Let's just get it. Now I can use here. Yeah, keep going in orange, I guess.
Question.
Yes. Oh, sorry, this is.
Did you forget to talk about the definition of topological?
Yes, it is. Thank you. So, I mean, this one. Or really
So, and also about
On the upper part.
But there is, thank you. Yes. Okay, so now we use here. What is this? So I can write it as dB AA as the best index improvement. And I add and subtract the A, AB. dB, sorry. And this here is going to be equal to, I have this argument with a minus 1 to the I. I mean, usually this is just, you see that this is just the epsilon BAC. I mean, this is just the curl of A, so what I get is epsilon BAC ER, which is nothing but minus 1 to the I DC. That's this part. And it is. So then, if I come back here, that's actually cool. I don't need more explanations. Minus 1 to the I, D dot A minus 1 to I D. And then we have here two terms plus. There is, maybe I just color coded. So now, from this last term here, there are two contributions. There is this contribution here, which has somehow a cross product. So the cross product term looks like this. 1 over S L dot P dot plus D. So this minus 1 to the I here cancels this minus 1 to the I. And then we have here a D dot, and a D, and an L, and an epsilon. And a 1 over S. So that's this. And then there is the other term, which is this guy here, this here, from here, and this one. But then you also see that here we have dA dot, and then partial A on A. Sorry, too many A's. So D lowercase a dot, and then partial lowercase a, uppercase A. So that's nothing but the total time derivative of the A. And so this guy here contracted to the A is just time derivative of A. And then taken together with this one here, what I have is just the total time derivative of the full combination here. So we get from this one together with this one is 1 over S, so plus 1 over S, d tau of L dot A of minus 1 I. So that guy is going to go to 0. This is just a total derivative. We integrate from 0 to beta. The fields have to be the same at the beginning and at the end. The manifold is simply connected. So this guy will just be the same. The whole bracket will be the same at time beta as at time 0. So this goes to 0. And the integral tau 0 to beta. We can forget about that. In the first term, this is nothing but, first term is S as the mean of minus 1 to the I, equals. Now I just go to the fields. Okay. Last thing is we need to evaluate this one, assuming that D is smooth. Now I would like to have this on the back part still. So I might just remove this part so far and keep writing here so you can still see the law there. So S top, so we've just seen S top is sum of all I distributing whatever over S. S the Zumino of the minus 1 I E of xi and tau plus 1 over L, 1 over S, that's the green part, L times E dot plus D.
And integration over the top.
And integration with
You should not integrate with the minus one.
integrate. Yeah, thank you. Okay, so we need to find out what happened to this main term. So this is another loop calculation. Okay. So what we use here is that there's a main term of minus 1 to the e is minus 1 to the I as Vesumino of D modulo 4 pi. What's the best way to see this? Yeah, it's probably the best way to see this is this representation here. So to get the minus 1, the theta goes between 0 and pi all the time. And you get a minus 1. So this is how you get this minus 1 theta. Or differently said, independently on the orientation of D, A is such that it will point outwards. You get a minus 1 to the I from the end of. So using that, we have sum over all I and only the odd ones is the Zumino of the I d of xi plus a tau minus d of xi tau. And so when I is odd, we have a minus 1, sorry, minus s of d of xi tau. This is the s as in. And so we sum over only the odd sides here. We get the minus 1 here, and then odd plus 1 lattice vector is 1 lattice spacing is even. And now we can use that these here are slope variables. And what we use essentially is the same thing as what we just used before. So we use that this guy here, we write this here as d of xi plus d of xi plus a tau minus d of xi tau. I've added and subtracted this thing. This here I can write, let's call this here delta d. Delta d of xi. Which of course is nothing but a times dx d of x tau to leading order. So now I plug this in, and what I do here is, again, I have here in the argument of the Vesumino, I have d plus something. So I can use, again, the very same calculations, but instead of having L over S, I have this delta d. I will of course not do it again, but I can use, so this guy here is going to be cancelled by the second term here. The red term is anyway 0. So we only keep this here, but instead of L over S, we get this delta D. So what we get here is, okay, I write it out. It's the sum over I odd. And then we have here this expression, which is the green one over here, sum over d tau. Integral d tau. Then we have delta d of x, I, and tau times d dot cross d. So this was my side calculation. And now I can take, here I take this expression, the dA. I replace this A here with this guy here. I have A sum over all I odd. I'm going to replace it by an Riemann integral, but keep in mind that we're only summing over the odd sides. So what we have is only half the dx.
Yes. Factor of S is missing from the no?
So here I have S resumino of d plus delta d.
Yeah.
Here I calculated S resumino of d plus L over S.
Yes. Okay.
So therefore, whenever I see L over S,
Yes.
I replace it by delta d. No extra S.
Yeah, but then there is a leading S in front of the Westrino term.
That is.
I mean, it's actually missing in the coordinate
Yes,
representation.
so we have, it's missing here, and then only that's positive I is missing.
Yeah.
So this guy here from I S. Thank you.
And it's also missing in the coordinate representation of Westrino.
That's also right. Thank you. Okay, so we're done now. We've calculated this topological term to leading order 1 over S. So we get this I S half integral dx integral d tau dx d times, so we can call it d prime if you want, d dot cross d. Yes. Plus L over S d dot cross d.
Yeah, but then the factor 1/2 does not appear in front of the L term because there was not splitting into order.
Let me see if I have everything else. I L. Yes, exactly. Okay, I'll write this down again in a second to discuss everything. I can remove this, I guess. This. This. Okay. are. So we have Js squared A over 2 B prime squared plus J 2J over A L squared. This is copying from here. Then we have this thing here. Plus I over A L dot D dot cross D. And then we have this last term here, I S half, I S half. Now actually I like to shuffle this usually, so I write it as D dot D prime cross D dot. This is just a cyclic permutation. This part here, when it's integrated over, we call this here as theta, and we go into that later. So this is essentially the definition of S theta once you integrate over it. And this here, what we now do, so we see we have these L's, which are massive objects that a mass which is given by J over A. So on sufficiently long length scales, given by the adherence length, you should integrate them out, they have no impact, and we get from it a dynamic circle. So yeah, maybe I just skip this. So you just do a Gaussian and you integrate over L. Essentially, for those of them that have done this, you complete the square here. And you get a term which is sort of D dot cross D squared with a prefactor which is essentially 1 over J and something. And then you will see that this D dot cross D squared is nothing but D dot squared. So what you get in total is half integral to tau equal to x. So then we have d dot squared over b plus b prime squared plus s theta. I have introduced new parameters k and b. The k is called typically the stiffness. K is S half. It's dimensionless because what you see here, for example, here this has two time derivatives, but then it has meter per second in the denominator. So the whole thing here has dimension of 1 over length, 1 over time. So the prefactor will be dimensionless. And what's the dimensionless thing that we have around? This is S. And now you're also not surprised that when you derive the fluctuation of the goal modes, determining about the semi-classical limit using a small parameter, which is 1 over S in our case, one of the small parameters is the prefactor. This was, I think, your question essentially, how strong this thing will fluctuate. It's given by K.
Why were you able to integrate over the L? I mean, why were you able to integrate out the L?
So the L's a priori are, of course, assumed to be small, but here you see that the maximum value that the L can take before this thing blows up is something like A over square root A over J. They are massive, and on length scales, there's an effective length scale you can get from here, or an effective time scale. If you're interested at the long wavelength, long time limit, or low energy limit, these guys are not important. They're massive. Same way as we usually discuss it. Just have this picture. then renormalizing their coefficients. But here they also give it actually here, if the dot term comes entirely integrating on these L's, I mean the L's themselves have an impact, but they sort of can carry the information about the dynamics of these. So the dot term comes from there, and the velocity that you get from this procedure is actually 2ASJ. Does it answer your question?
Well, maybe your explanation is right, but as far as I thought, we can integrate L out just because it's Gaussian integral and it's very simple.
That's right, but it's in principle true. But the L's, I have an assumption in the beginning on these L's here. The L's should be small anyway.
And perpendicular to D.
And perpendicular to D also. Oh, well, this means just that there are only two, so these are not three integrals, there's two integrals.
Yeah, right.
But then also additionally, the fact that they are small is encoded in this J array.
Yes.
Okay. So what we have now is we have this action here describes spin waves about the about the Schnell state. So we start with the Schnell state and then we look at smooth configuration changes and how they propagate through the system. They have a specific speed, which is given by ASJ. And they have a stiffness, which essentially tells you that when you wiggle here, how strongly will you feel over here. Good. Now, what does this S theta do? S theta is I as half integral over tau and dx d dot d prime cross d dot. And this is nothing but I 2 pi s, and 2s is called theta. And you get d tau, and then this is topologically invariant in d. So if you wish, I can divide here by 4 pi, you can multiply here by 4 pi, and this is called empty. What it measures is the number of skirmions in the system. So we have here a space-time. I don't remember if it's an answer to somebody in the previous lecture. So we have space-time here. So this is, let's say this is x, this is tau. It's compactified in tau direction. This is also compactified in x direction. So periodic boundary conditions in x direction. And there are three configurations which are topologically non-trivial. So this is my spacetime, and this is my spin. And let's say on the boundary, everything has to be the same, right? Because the boundaries are identified. Let's assume that even this one has to be identified with this one. So then everywhere outside here, the spin points up, but there are configurations where this goes in. This is called a skirmion. This corresponds to, I had this analogy of wrapping an orange with a towel. I think it was to you. So that's wrapping in once, so when you have a skirmion. And then there are double skirmions, etc. And this guy measures the number of skirmions in the system. Measures number of skirmions in the system. A way to see a skirmion maybe is if you think about our space-time. It's actually a torus, but let's assume it to be just that if you identify this also we follow this, then it's essentially S2. So we're mapping from S2 x tau to D, which is also an S2. So it's mapping from the sphere to the sphere. And what you can do is, if this is my space-time, I can say at each point in my space-time I have a unit vector, and the skirmion corresponds to the hedgehog. So if I have a configuration where I have hedgehogs, then this is good. This is another way of saying what I just said using the antenna. Yes?
What does the meaning of the L specific mean? Does it mean that we don't observe such L interactions in the low energy physics, and then only there are only formulas.
They will only give you sort of something like the interaction of these guys. The else will only mediate an interaction. It's like a meso.
But I will not see them themselves. But I will not see them themselves.
You will, unless you go to like high energies, you will see them. Okay. So this thing is so this is an example I told you last time about these different types of logic terms. This is the third type where we have an integral which is quantized. The prefactor called theta here a priori need not be quantized, it is quantized in this situation here. In our case, theta is either 2 pi times an integer, 2 pi times an integer, or s even, s integer. Or it is pi plus 2 pi an integer for s c plus a half. Well, I guess we don't have negatives. And then since this here is just a number, 1, 2, 3, 4, and this is 2 pi times an integer. So this is e to the I 2 pi times an integer for integer spin. So for integer spin, the effect in the bulk of this term here is absent. It does not contribute. So what you have to do in your partition sum, you have to integrate over all possible D configurations, including those with the skirmions. But those with skirmions and those, so the sectors with skirmions and the sectors without skirmions, they contribute in the same fashion if S is an integer. However, when you have an odd number of skirmions in your system, and the spin is half integer, the situation of odd number of skirmions gets a relative minus sign as compared to those with an even number of skirmions. So what I'm trying to say is that skirmions are topological objects. There's 1, or 2, or 3, or 0 in it. I cannot adiabatically change my field configuration from 0 to 2. And these are different topological sectors. When I evaluate my partition sum, I have to sum and integrate over all configurations of these. That in particular means that this here, integral to d to the minus s. This is going to go into all these, and maybe I write this here explicitly, s kinetic minus s theta. This is going to give me sum of all topological sectors. And now we have here an additional d. I'm not sure to write explicitly, but maybe it's a d delta d or something like this. So we can take a d, which is topological configuration, and then on top of it, smooth variations. That's what we integrate here. Then we get e to the minus s kin. And from this one, I get minus 1 to the number of skirmions, which is this thing that I integrate the sum over here, topological sectors. So these are number of skirmions. Times 2s. So when s is integer, this does not contribute at all. But when s is half integer, if the number of skirmions is odd, then you get a minus sign in your partition sum, and when it's even, you get a plus sign. And they mutually cancel, and that has implications on the renormalization of flow, which I'm not going to show here. But essentially, the conjecture is that when you do renormalization group study of this object, and you study how this K flows, how it gets quantum corrections, how your stiffness actually decreases as you go to longer and longer length scales. This flow is altered by the presence of this topological term. So when S is integer, topological term has no impact, and K just has a randomization group flow, which is as you flow towards infrared, K goes down. That means the stiffness goes down, and that's nothing but Mermin-Wagner theorem. It will ultimately go to 0 and you have no stiffness, so if you wiggle here, you will not notice it here. But this sort of interference effect between the different topological sectors prevents this to go all the way down to 0. That's the idea behind it. Okay, and that's the Haldane conjecture. So maybe I should write it out once. Somewhere.
May I ask a question?
Yes, please.
So, if we write naively the partition function in the case of even spin, where this -1 to the 2s times the number of square does not appear, it's tempting to say that we can just throw this theta term away completely and remain with the theory of just, let's say, a vector with this action. Is this correct?
In the model, it's correct, but not if you have open boundary conditions.
Okay.
And this is something interesting. So Haldane conjecture. This even spin, sorry, integer spin, integer spin chains are kept. And in fact, if you know how to solve these normalization group equations, we'll find out that this gap is going to be j to the small in this case, but here we get it from our g, j's, gap, e gap, is j e minus k. It's exponentially small because this is logarithmic. In 1 + 1 dimensions, this is logarithmic for g. But half integer spin and the half integer, I mean half odd integer. So half, 3/2 half odd integer. Spin chains. Critical, which means scatters. And in fact, this was known at the time of Haldane's work, early 80s. It was known that spin. The surprise is actually this one. This is what you would expect from Mermin-Wagner, right? This is Mermin-Wagner. Mermin-Wagner. This is what was known by Bethe in the 30s. Bethe Ansatz, the first Bethe Ansatz paper was in the spin chain, spin on action. And it was known that it is critical. So, yeah.
Could you just repeat the argument for this again?
The argument for this is, okay, it's sort of a guess. It's a conjecture. We saw some ways to see this. Okay. It depends on what you want to calculate. But let's assume when you want to calculate a physical quantity such as the spin coordinating. To do that, you have to put in the path integral here. Expectation value, I mean, the correlator means put a d as space time position here, and a d as space time position here, in front of the exponential, and integrate over all of the. It involves also integrating of the d's which have the Königs. And the fundamental difference is that in the case of integer spin, the effect of König is absent. So you just integrate over all of the spin waves, and then essentially what you restore is just by Mermin-Wagner theorem that there is no longer an order of d. However, there is a topological effect that is actually not present in, it's only present because it's 1 + 1 quantum theory. It's not present in 2 + 0 classical theory. So it's a theta term. This theta term changes the contribution of the sectors where you have an odd number of Königs. in such a way that sort of even an odd number of experiments sort of cancel out, and the fluctuations effectively the fluctuations there cancel out. And therefore you do still keep a finite spin-spin correlation function. When S is half ordered to a half spin. So it's a conjecture based on the presence of the different sign that these experiments acquire in the presence of spin 1/2 and spin. I know this is a very deep conjecture, right? This is part of a Nobel Prize.
And long-range correlation is related.
So you know, I mean, what you usually have is when you have real long-range order, you have to look at the correlation functions, and they saturate if you have real long-range order. What you actually get here is you get algebraic decay. That's the best that you can actually get in first dimensions. You cannot get actual long-range order, even in the presence of half inches. That's what this critical means. It's a power. A critical, means gapless. Yeah? And we will see it maybe half a lecture tomorrow for this sequence. Let's see if I get there. Yes?
Sorry, I just don't think you're saying this is Norman binary in the sense that you have a gap, so then you have finite correlation length, or
That's a different way of saying it. I put a gap, yeah, but you say I prefer to speak about energies and you prefer to speak about length scales, but it's the same thing.
just meaning that you have finite correlation, which is no longer in order.
There's no longer so much. And the correlation length is something like 1 over energy, actually it's V over energy. The correlation length is going to be exponentially small, exponentially large if the K is large, which it is in R. I mean, the RG is controlled in large K. The fixed point of RG in the presence of this theta term is going to be at K order 1, which is outside the regime of perturbative RG, so we cannot really access it. But we do know what spin 1/2 chains correspond to. We do know the CFC that describes it, which is SC2 level 1. So we know everything about it.
Can you please pictorially explain how scalar's like?
Yes. Well, I tried to explain it using the iPad, which I thought was. Can I do this again? So the condition is that the boundary condition is, so you have two-dimensional spacetime. And the boundary condition is that your spins are taking the same configuration everywhere at the boundary. So let's say up. The Skirman corresponds, so nothing is corresponding to it anywhere in this space-time we have just up. That's the minimum energy actually. But then there are configurations where this goes in and then goes up, out again. That's a Skirman. Now if I took my iPad and I made it a ball, then this would correspond to this thing here. My boundary of the iPad is down here, well, maybe my boundary of the iPad is this here and it corresponds to up. And my center of the iPad is this here, so I can look at this. And I wrap it. And then the center is this, that's where it points down. So it looks like a hedgehog. If you compactify your space-time and really represent it like a sphere, it looks like a hedgehog. Yes.
Maybe go into this last week. Why anti-ferromagnetism here?
So for ferromagnetism, you wouldn't get these. You wouldn't get such a term. The Resonian term would just drop out. There is nothing. Also, in ferromagnetism, the spin waves are not linear, quadratic, and things different. So anti-ferromagnetism is somewhat important. Okay. Now we take open boundary conditions. Let's take spin 1 chain with open boundary conditions. Open boundary conditions. So I want to undo what I did before. In the spin 1 chain, the bulk we figure out that there's a kind of gap, and equivalently, as we just discussed, there's a coherence length which is going to be proportional to A e to the K. Finite coherence length. And it therefore makes sense to sort of re-discretize the system. That's what I want to do now. To get back to a lattice problem. Yeah? So essentially what you can do is you can think, anyways, in each chunk of size psi, all of my d's are going to move together. But if I move by one chunk, then they will do something different. And I can sort of, I take my action here, the one up there. I make chunks out of it. So the S, so the S without the S without the theta term, the regular part of the action, you get to the theta term in a second. It will thus be chi half, k half, into the tau. Now I make chunks of size. So these lines now goes over chunks of size psi. So that means that this guy is size psi over v I dot squared minus v over 2 psi I. Now this is nothing but taking the, I cannot do it this way, plus p minus di plus 1 squared, and probably I have in that case extra 4 or something like this. Add a k half here, and that's a g naught. And again, so the only part that's really adding here is, the only part that's really important here is this is going to be proportional to minus 2 pi. So what we had is we had a spin chain, everything was going to, so the d vector points always in the same direction, right? So I've already absorbed this, I've absorbed the Mel behavior into this minus 1 pi, so the d always points in the same direction, and what I'm trying to say is that there are chunks of size psi where they sort of move in parallel. This is blue screen here, but maybe to illustrate it, this is the next psi chunk. Yeah? All of this is size psi. Okay. And in particular, when we have low energies, we can actually drop this one, but okay, we will get there later. And now the question is, what happens at the boundary? S theta. So S theta, as we know, in the bulk it has no impact. But what about the boundary? At boundary. So maybe I need to do again a side calculation, which are in blue today. So what we need is we need to go to tau dx of d dot d prime cross d dot. So when you use spherical coordinates, what you find, just plug it in. Now dx, you find theta prime phi dot minus phi prime theta dot sine theta. So we can write this here as integral tau dx of dx cos theta phi dot minus tau cos theta phi prime. By the way, effectively this is sort of antisymmetric. That's very typical because in differential geometry language, what's done effectively is that you're putting back a measure from one manifold to the other. And these antisymmetric combinations here, this is nothing but different differential forms. For those of you interested in differential geometry. Okay, so then let's write this part here. So this here we write as dx cos theta phi dot minus dx tau phi. And this here we do the same thing. Here we write tau cos theta phi minus tau. Yes, sorry, I missed the cosine. I will add it in a second. So minus cosine theta tau dx phi. And I really forgot the cosine here. Where's the cosine? We use that we do have periodic boundary conditions in tau direction, so this guy goes to 0 upon integral of tau. Just a little bit. So we get integral of tau dx cos theta dx cos theta phi dot. This is this part here. And then we get minus cos theta. And then we have here dx d tau on phi. Commutator, right? So here we have minus dx d tau phi, and here we have minus so plus d tau dx phi. So we have a commutator. So this guy also goes to 0. Phi is sufficiently differentiable, etc. So we just take the total, this here, all that we get. Now we get a contribution from this total derivative in space, and we get a contribution near 0 and a contribution near L. So using that, what we have here is this. We get S theta, in the case of open boundary condition, gives you I S half integral d tau cos theta phi dot, all of this at x equals L, minus I S half integral d tau 0 to beta cos theta phi dot at x equals 0. Mind you that you can do this procedure only under the assumption that it makes sense to consider the boundary separately from the bulk, because there is a gap in the bulk, so nothing will really propagate to the bulk. So we can only do this when S is integer. Excellent, that I kept this all the time. So what you see now is that if you, for example, assume you start with a spin 1 problem, spin 1 chain, and what we get that the boundary is a topological term, which looks like the Mesomino term that we got for the spin 1 half particle. So this S here and this S here are not the same. I mean, this is the general S for arbitrary, calculation of the path integral for an arbitrary spin S particle. Here, we calculated the boundary action for a system with integer spin, which the bulk is kept anyways. We know that the bulk is kept. So at most, something happens at the boundary. And we find that the boundary, let's say for spin equals 1, behaves like a spin 1 half particle. So like this. Behaves like spin 1/2 particle. Behaves like S1/2 edge states. You keep in mind here that S integer, otherwise our procedure doesn't make sense. So what we would get from here is for spin 1, we get spin 1/2. That's something we already saw for AKT. For spin 2, we would expect spin 1 edge states. That's actually incorrect. So this gives you the correct answer for spin 1. For spin 2, you might be tempted to think that there's a spin 1 edge state, but the spin 1 edge state actually can be trivialized in the sense that the spin 1 essentially corresponding to 2 spin 1/2s, they can go into a trivial state. We've essentially seen this from the symmetry fractionalization viewpoint, that there are only 2 different possibilities to represent these symmetries. But still, I think it's, I don't know, when I first learned this, I thought this is very cute to see how this spin 1/2 comes out from the P theorem. Okay.
So once again, what happens for s equals 2?
So the idea behind this is that for s equals 2, you, one way of thinking of it is that you have 2 spin 1/2, spin 1s, and you get spin 1/2s at the edge which can mutually annihilate. Essentially, the statement is that you can find terms which are symmetry allowed, and so from this you would think you get a spin 1, so you get a triplet. And what I'm trying to say is that there are terms which are symmetry allowed that you can add to the edge action, which sort of will gap out 2 of these. Leave a unique constant.
And the similar situation happens for all the higher spins?
So it's only for 1, 3, 5, etc.
Ah.
Because for 3 again it's the same thing as 2 plus 1. So the statement is essentially that there are only 2 different possible topological phases. Which is what we saw from the symmetry fractionalization. We only saw 2 different ways of representing the rotational symmetry. Remember we did Z2 cross A2 and there were 2 ways of doing this. There is another aspect of the whole story to conclude this, namely that here I've looked at a one-dimensional problem, and essentially the idea was to reproduce what we already knew about symmetry-protected topological phases using field theory, and we saw that the symmetry-protected topological phases are encoded in the possible theta terms and the corresponding boundary states that you can have in the field theory. This was one dimension, and the target manifold was S2, but you can generalize this to higher dimensions and maybe a target manifold which is also bigger, and you can have theta terms. So it turns out that you can classify, as you saw, we have tried to, I didn't do the full classification, but we argued that you can use the symmetry fractionalization to classify with certain König SPTs. And you can also use the field theory and look at which possible theta terms. And while these communities don't really speak to each other, that's essentially also what probably Pasha will tell you from this classification of fermionic SPTs, so fermionic topological insulators, using the diffusion theorem. Again, you will look at the theta terms of this type, only in more complicated manifolds, and then I guess it will also show you how a theta term in the bulk implies a Bezzolino term on the edge. I have classic examples in one module.
Are there any questions? Okay.
All right.
Thank you.
Thank you.